Welcome. Today we're going to talk about chapter 12. And last week we did a summarization, and that's where we found statistics from the sample or survey data we collected. What we want to do next is generalize those statistics that we get from our survey data to the general population. And so these are the techniques that we'll be talking about in this particular lecture. So generalizing is using the sample error and establishing an interval for the range we expect to find in the population with a given level of confidence. So we refer to a sample finding whenever a percent or average or some other analysis value is computed with a sample's data. However, because the sample error involved, the sample finding must be considered an approximation of the population fact. So if we took a census of the entire population, then we would know the true value. But since we have a value from our survey or sample data, we can estimate the actual population value. When a researcher follows proper sampling procedures and ensures that a sample is a good representation of the target population, the sample findings are the best estimates of their representative population facts. But again, they'll always be estimates because they're going to be hindered by sample error, which is the variability that we get when we choose samples. We may get a different sample if we ran the survey again, take 1,000 people this time, get a certain set of statistics. We run another 1,000-person sample, we're going to get slightly different statistics. So generalizing is estimating a population fact from a sample finding. We'll be making an inference about the entire group based on some evidence, but not complete evidence about that group. So there's two things that will affect the results, and that's going to be the variability and the sample size. So here we have a table that shows how we might generalize our sample findings to the population of all Chevrolet buyers in the case of a sample of 100 versus another sample of 1,000. So with the 100, notice how much wider or imprecise the interval is for our estimate of the population. So in both cases, we found fairly similar findings. 33% say they are dissatisfied with their Chevrolet in the 100 sample size. With the 1,000 sample size, we find 35%. But notice the range when we try to generalize this to the overall population. We get a 24 to 42% range with the 100 sample size, and we get a much smaller, or in other words, a more precise interval for the overall population estimate of 32% to 38%. So estimation of population values is also called parameter estimation, because we're estimating a population parameter. The denotation of population parameters is done with Greek letters, such as pi for percent or mu for mean. Sample findings, on the other hand, are denoted with lowercase Roman letters, such as p for percent or x bar for average or mean. A confidence interval is a range, a lower and upper boundary, into which the researcher believes the population parameter falls with an associated degree of confidence. And typically the confidence levels are going to be 95 or 99%. And often in marketing, it's going to be 95%. So this is how we calculate our interval for a percentage estimation. P is going to be our sample percentage. Q is going to be 1 minus P. Z is going to be our Z value for the 95 or 99% confidence levels. And of course, that whole term P times Q divided by N and then the square root of that is the standard error of the percentage. So at a 95% confidence interval estimate, we're going to use a Z factor of 1.96. And we multiply that times our standard error, P times Q divided by N, and then the square root of that. And that becomes our limit. And then we take P, the percentage we found in our sample, and we subtract the limit from that to get the lower bound. And then we take P and add the limit to get the upper bound. N is sample size. So the first step is the calculation of P. And of course, we do that with a simple operation in our spreadsheets on our data set. And let's say in this case, we found it to be 33%. Q is going to be 1 minus P, or 100% minus P. So in this case, Q is 67%. Our sample size is 100. So we're going to take the square root of 33 times 67 divided by 100, and we get a standard error of 4.7%. Then we multiply that standard error by the Z factor to get our limit. And the limit here is 9.2%, 1.96 times 4.7. Our lower boundary is then P, the percentage we found in our population, minus the limit. That gives us 23.8. The upper boundary is going to be P, the percentage we found in our sample, plus the limit, or 42.2%. And here's a comparison of the ranges at the 95 and 99% confidence level. At a 99% confidence level, we use the Z factor of 2.58 rather than 1.96. And this will give us a wider confidence interval. In other words, to be 99% confident instead of 95, we have to increase the range of our confidence interval. So to interpret this, if we take multiple samples, this particular case, we had 100 people. Let's say we just kept doing samples of 100 people over and over and over again. we would get a sample percentage that would vary. Sometimes it would be 33%, sometimes 35%, and so on. But because of the central limit theorem, we know that the sampling distribution is going to be a normal curve. And with that, we can use the mathematics of a normal curve to help us determine the confidence levels of our sampling. Now, variability also affects the width of our confidence level. So when we have less variability, then our standard error will be smaller, and we will have a smaller confidence interval. As shown on the right, we have a confidence interval of 56 to 64% when our standard error is 2%. Whereas if our standard error, because of increased variability, rose to 5%, our confidence interval jumps from 50 to 70%. Now, we can use the Excel data analyst to compute a confidence interval, and we'll be doing a workshop on Wednesday where we actually use the raw functions in Excel to do this, but I just want to show you how to do it with our Excel data analyst tool. So again, on the next class, we'll go over how to do it using direct Excel functions. So let me pull up a worksheet. And there we go. So here's our Advanced Automotive Concepts survey results. And to do a percentage confidence interval, what we'll do is go up to Excel Data Analyst, go to Generalize, Confidence Interval, then Percentage. And in this particular case, we're going to look at primary vehicle type right here. And let's look at an SUV or van. So my percentage in the survey is 25.8% of the survey respondents owned an SUV or van. We had a standard error of 1.4. Multiplying that by the 1.96, we get a limit. We subtract that limit from 25.8 and get a lower boundary of 23.1. We add the limit to 25.8 and we get an upper boundary of 28.5. And here's some slides that show exactly how to do that. And we get the results that I just mentioned. This is an earlier version of Excel Data Analyst, and it didn't include the standard error in its print. Okay, so that was how we figure out the confidence interval for a percentage. What if we have a quantitative variable and we want to get the population average instead of percent? Well, here's the formula for that. Again, we use our Z value for 95 or 99% accordingly. So typically we're going to be using 95%, which is 1.96. we're going to multiply that by the standard error, which is S, the standard deviation, divided by the square root of the sample size. So again, it's the same pattern, the Z factor times the standard error. What's different is with a quantitative variable, we calculate standard error a little differently than we did with the percentage or categorical variable. Then of course we get our limit factor by multiplying the standard error by the Z factor, and we subtract that from our sample average to get the lower bound, and we add it to our sample average to get the upper bound of our population estimate. So let's go through this step by step, just like we did for our percent calculation for categorical variables. So here we're going to do the confidence interval for an average for a quantitative variable. So X bar is the sample average. Then we have the standard error times the Z factor of 1.96 for a 95% confidence level. So the first step we do is calculate the average of the metric variable. And once we get that average, then we calculate the standard deviation of it. And of course, we'll use the standard deviation to calculate the standard error. So once we have the standard deviation of the sample, then we divide that by the square root of the sample size, and we get the standard error. The limit is we multiply the standard error times our Z factor of 1.96 for 95% confidence level, and we get our limit. And in this case, the limit is, 3.9 minutes for this particular problem. The average was 45. So to get the lower bound estimate for the population in general, we subtract the limit from the average to get 41.1 minutes. To get the upper bound, we add the limit to the average to get the upper bound of 48.9 minutes. And of course, we see those calculations right here. So we get our lower bound of 41.1, upper bound of 48.9. And again, we can compare this. That was a 95%. We can compare that with a 99% confidence level by using the Z factor of 2.58. And that gives us a less precise interval, a wider interval of 39.8 to 50.2. So what this means again is if we repeated our survey over and over and over again, and we took the average time for this, again, New York Times survey, we took the average time, we'd get a slightly different average, but it would be between 41 to 49%, 95% of the time. And again, this is just based on the mathematics of the normal curve, because the sampling distribution becomes a normal curve. So let's take a look at how we do this in Windows with Excel Data Analyst. Again, on Wednesday, we'll handle the case for Mac users as well as Windows users. You don't have to use the Excel Data Analyst in Windows. You can go straight to Excel functions to do the same thing. But let's take a look at it since it is included in the text. Okay, so now we've got our worksheet again. And what we want to look at is gasoline emissions. So we're going to come up to generalize, average. Then we'll look at gasoline emissions contribute to global warming. So we'll select that variable and click OK. And we get an average of 4.8% of the people agree with this, with a standard deviation of 2.3. So if we calculate our limits and subtract them from the average, we find that between 4.7 and 5% of the overall population would agree with that particular statement. Okay, let's go back. And here we see the results for that. Okay, any questions on this?